Hello, today we're going to talk about what we call type B synthesis reactions. So we would put this on our types of reaction notes as, again, a type B synthesis. Now this one's a little more tricky than a type A synthesis. In a type B synthesis, we have a metal oxide reacting with a non-metal oxide. And what they're going to create is an ionic compound, again, one ionic compound, with a polyatomic ion, PAI for short. All right. Now, this polyatomic ion is going to be a polyatomic ion that you know already. It's not going to be a crazy one that you haven't seen before. It'll be one of the polyatomic ions that you've seen. Now, let's think about this. We have a metal oxide and a non-metal oxide. What types of compounds is a metal oxide, and what type of compound is a non-metal oxide? Are they ionic or covalent? So I'm going to let you hit pause a second and try to figure that one out. Okay, so in our non-metal oxide, hopefully you realize that this is your ionic compound because it's got a metal in it, right? And anytime you have an ionic compound, you're going to hear me say this a lot throughout the video, we have to check the charges. Okay, because the charges are going to rule here. In a non-metal oxide, it's covalent. And that means we're going to use a prefix system. Now, don't crisscross the prefix, only crisscross ionic compounds. Now, these are non-redox reactions. So, they do not form the oxidation numbers don't change, but you still have to check the oxidation numbers, and that's going to be the key to figuring out what that polyatomic ion is. I'll say that again. You're going to have to figure out the oxidation numbers, all right, and that will tell you if you got the right polyatomic ion. So even though it's a non-redox reaction, you still have to do oxidation numbers, okay? So let's try going through some problems here. So a typical metal oxide, non-metal oxide reaction. I would give you the metal oxide first, then the non-metal oxide. I'm going to give it to you in that order. I'm not going to deviate from that. So I could give you the metal oxide first, or sorry, the non-metal oxide first, then the metal oxide. I'm not going to do that. So it'll always be the metal oxide, then the non-metal oxide. All right. So let's say we have calcium oxide. Again, oxides have oxygen in them, all right? And carbon dioxide. So calcium and oxide. So again, these things are going to have charges. So you should know by now that calcium has a 2+ charge and oxygen has a 2- charge. So it's going to create the formula CaO. Carbon dioxide, no charges. You just use the prefixes to determine the number of elements in that compound. So what polyatomic ion has carbon in it? Now, this is kind of an easy one because you only have one polyatomic ion that has carbon in it, and that is carbonate. And carbonate is CO3 2 minus. All right. Now, the stem of carbonate, or what makes it carbonate, is the fact that it has carbon in it. I call that thing the stem. Okay. Your polyatomic ion will have the same stem as the nonmetal oxide. Okay. So this is the thing that determines what type of polyatomic ion it is. Not that, this. Okay, it's the nonmetal oxide. I'll say that again. So we are going to create a compound that has a metal in it and carbonate. Well, this is where the metal comes from. Okay, so we are going to write the two things together. CaCO3. So again, calcium has a 2 plus charge, and carbonate, we just said, is a 2 minus charge. So when we combine these, they combine into a 1-to-1 relationship, making CaO. Now, how do I use oxidation numbers to tell me if I did this right? Okay, so your compound that you make will have the same oxidation number as the stem of the nonmetal oxide. Oh, I know that's a lot to take in. I'll say that again. The oxidation number of these two things, these two stems, essentially will be the same. That's kind of what I just said. All right? So they will have the same oxidation numbers. And that's how you tell. That's how you basically figure out if you did it right. Okay. So, well, what's the oxidation number of CO2? So, again, carbon dioxide is a neutral compound, so it's going to have to add up to 0. We know that oxygen, and at least for everything that we're doing, is a -2. So that makes 2 of them a -4, and we'll call carbon X. So what's the oxidation number of carbon here? Well, it's got to be +4. Well, hopefully, if we did this right, the oxidation number on the carbon of the CO3 should be +4. All right, so the stems need to have the same oxidation number. Now, I tell people, well, pull out the polyatomic ion. Okay, don't make it a part of the compound because it makes it too difficult of a job. So this thing has to equal -2. All right, -2 for the oxygens, that's a -6. So what does X equal? Well, X has to equal 4 plus to make this a true mathematical statement. So our oxidation numbers are the same. That's telling me that I did it right of both stems. All right, now we do have to go balance it. Okay, so that has to happen. In this particular reaction, I believe this is balanced already. You got 1 Ca, 1 Ca, 1, 2, 3 oxygens, and 1 carbon. All right. Now, as far as the states, so get the balancing done. States are pretty simple for this. This will always be a solid. This will always be a gas, and this will always be a solid. So it's going to be solid, gas, solid. All right. Again, in these reactions, you're going to have 3 things. All right. I know it's a lot to unpack. Okay. So if again you want to rewatch this part of the video again before we go on to the next example, please do so. Okay, so um, the next metal oxide will be potassium oxide. And sulfur dioxide. Okay, so let's just pause the video and try to write these reactants out. That's all you need to do for right now. Just write the reactants out. Okay, welcome back. Hopefully we understand potassium oxide is our metal oxide, right? And again, this is going to be ionic. So K plus and oxide is O2 minus, and we get the formula is K2O. Again, sulfur dioxide is covalent. You don't need to write that unless it helps you, then by all means, please do so. So sulfur dioxide is SO2. All right, so this is a little more complicated one because we have two polyatomic ions with the stem of sulfur in it. You got sulfite and we got sulfate. Okay. So which one is it? Which polyatomic ion is it going to make? Is it going to make the ITE version or the ATE version? So we have to figure out the oxidation number of that sulfur right there and find out which one of these makes that same oxidation number. So let's do that. So pause the video and figure out the oxidation number of sulfur right here. Okay, welcome back. So again, this is a neutral compound, so these are always going to equal 0. 2 oxygens, 2 times a negative 2 is a minus 4. So just like the CO2, this has to equal plus 4. So we go and look which one makes an oxidation number of plus 4. So let's say we do sulfur first. All right, SO4 2 minus. So that's a minus 2. It has to equal 4 times a negative 2 is negative 8. So we'll call sulfur 1x. So this has to equal plus 6 to make this a true mathematical statement. So our stem here has to equal plus 4. So guess what? It's not sulfate. Well, just to make sure, let's go do sulfite. Sulfite, again, negative 2 times 3 is a negative 6 minus 2. So we'll call that for the sulfur, the stem, x. So again, to make this a true mathematical statement, this has to equal a plus 4. So we are going to make the sulfite version. And that's what oxidation numbers tell you here. All right, so it's going to make K SO3. Now, I always, since this is an ionic compound, I always have to check the what? You guessed it, the charges. All right, whatever the charge of the metal is here, it's going to be the same on the product side. So again, I'll say that again. Whatever charge the metal is going to be on the reactant side, it's going to be the same as the product. So potassium is plus 1, because you could have transition metals too, right? Sulfite is 2 minus. So when I write these together, K2SO3. So again, this is stuff that you've done before. We have to go back and check the balancing. 2 potassiums, 1 sulfur, 3 oxygens on this side, 3 here. Okay, so again, like the other problem we just did, it's balanced. It's not always going to work out like that. So just be aware. And again, I said like the states, solid, gas, solid. Okay? try one more. So the next one, we're going to have magnesium oxide and diphosphorus pentoxide. Okay, so these are my two reactants. So again, pause the video, see if you can at least write the reactants out. Welcome back. Again, our ionic compound, magnesium, 2+ charge. All right, oxygen, 2- charge. So it's going to create some MgO on a 2-to-2 relationship. Diphosphorus pentoxide, P2O5. All right, so again, this is our stem. Our stem is phosphorus. So what polyatomic ions that have phosphorus in it? Well, you know we have phosphate with a PO4 3-, and we have phosphite. So which one of them has the same oxidation number as that phosphorus? That's the one you're going to choose. So we need to go figure out the oxidation number of phosphorus. Again, equals 0. 5 times -2 is a -10, and we'll call this 2x because there's 2 of them. So in this case, if you do the math here, x has to equal 5+. All right? So our polyatomic ion has to be 5+. So let's do phosphate first. So PO4 3-, again, this has to equal -3. Oxygen, 8 times negative, 4 times -2 is a -8. All right, phosphorus is one of them there, so we'll call that X. And if we add -8 to both sides, +8 to both sides, you get a X equal +5. So that's telling you that it's phosphate. So our ionic compound is going to be composed of magnesium, which still has the same 2+ charge, and phosphate, PO4 3-. So when I write these two together, I have to crisscross the charges, right? So we get Mg3 parentheses PO4 2. All right, now this one is not in balance. Okay, so we have 2 phosphorus here, we have 3 magnesiums, and 2 phosphorus here. So actually the phosphorus are in balance. So if I put a 3 here in front of the magnesium, that balances the magnesium. Again, like I just said, phosphorus, this is a multiplier, so that's 2 phosphoruses. Now, we have a total of 8 oxygens on this side. Right? 4 times 2 is 8. And hopefully, we have 8 oxygens on the other side. So we have 3 from here and 5 from here. That's 8. So another indicator that you did this right, it should not be very difficult to balance. Okay. And again, my states, solid, gas, solid. Okay, so again, no oxidation numbers are changing, but you need the oxidation number to figure out what polyatomic ion that you're going to pick. All right. I think we should just do one more with a transition metal in it. So iron 3 oxide. And dichlorine Sorry. Think about that one for a second, which one I wanted to do. All right, so again, pause the video and take notes. I mean, take notes. Hopefully you're taking notes as you're doing this. Write the reactants out. Okay, welcome back. So we should have Fe2O3. This iron here has a +3 charge. Oxygen's a 2-, and we have Cl2O3. Alright, this is a little more difficult one because we had 4 polyatomic ions that had the stem of chlorine in it, right? You had ClO4-, which is perchlorate, ClO3-, which is chlorate, ClO2-, which is chlorite, and ClO-, which is hypochlorite. So, pause the video. I want to see if you can find the oxidation number for chlorine and figure out which one of these we should use to create our ionic compound. Okay? So hit pause and figure these oxidation numbers out. Okay, welcome back. So, to figure out this oxidation number, again, we set it equal to 0. Okay, this is a -6, right? And this is 2x. So, in order to make this a true mathematical statement, okay, 6, 2x, x would have to be +3. So, which one of these has a +3 oxidation numbers? Well, let's pick out chlorate first. Let's see, just gotta pick one. And again, these oxidation numbers never change. So no matter what you're mixing it with, okay, as long as you know the oxidation number of that polyatomic ion, doesn't make it different what the difference what the metal is. As long as you know it, it's not going to change. So let's see, chlorate. This has to equal -1, so -6. Well, we'll call the chlorine will be X. Well, that has to be +5. So it's not chlorate. And if you figured it out, as you start to add less oxygens, the oxidation number of the stem goes down. As I add oxygens, the oxidation number of the stem goes up. So it's not that. So it wouldn't be ClO4. Let's try ClO2. Chlorite. So again, it has to equal -1. 2 oxygens. That's a -4. And chlorine is X. Well, X has to equal +3 when I add +4 to both sides. So this is the winner. Now, like I said before, iron is +3 over here, so it's going to be +3 in the products. So ClO2-, when I mix these two together, I get FeClO2, and I have to put a 3 behind it for this +3, crisscross, and I need parentheses here. Okay. So we have to go back and look at the states and balance the thing. So let's balance it first. So again, if we did this right, it should not be very difficult to balance. So we have 2 irons here, we have 1 iron here. So we put a 2 in front. Okay, we have the next, we go to chlorine. Okay, we have 3 chlorines times 2, that's 6. So I need to put a 3 in front of this. That gives me 6 chlorines. Now, we have a lot of oxygens here. And again, if we did this right, it should come out to be an even number. Or they should equal each other, I should say. So we have 3 oxygens from Fe2O3. And we have 3 times 3 is 9. So that's a grand total of 12 oxygens. So fingers crossed, all right, We have 12 oxygens here. 3 times 2 is 6, and 6 times 2 is 12. So we're good to go. And solid, gas, solid. And that's pretty much how you do a metal oxide and a non-metal oxide. Again, this is a little complicated stuff, okay, but again, it shouldn't be outside the realm of anything we haven't done before. We're just taking things that we've done and we're putting them together, okay? Thank you for watching.